This is exciting. We're going to kind of move past the review stuff. Like all chapter 0 was a review. We're going to move past that and into talking about limits. And limits are in continuity. And these are two really important concepts that will help us kind of understand the fundamentals or the basics we need to understand calculus. So let's just start with the limit here. Informally, a limit is a y value, which a function approaches as x approaches some value. So when we think about that, or look at the notation down here, right? It's saying as x approaches c, f of x, or my function, approaches L. So what that's really saying, as x gets closer to this value, so that is my x value that I'm getting closer to. As I get closer to that, the function, or the y value, is equal, what does the y value equal? And that is what the limit equals, right? So as x approaches c, your function f of x approaches the y value of L. So I think the best way to understand this is just by looking at these examples. So we have this graph of f of x over here, and it says what is the limit as x approaches -4. So what that means is I come over to my graph. As I get closer to -4, so as I go along my graph here, and as my x values get closer to -4, what we're asking is what does that y value get closer to? It sure looks like it's getting closer to 1. If I come from the other side, right, as x gets closer to -4, what's it getting closer to? Again, it's getting closer to 1. So from both sides, as x gets closer to -4, the y value gets closer to 1. Now notice over here, I'm going to do number 8 actually first. It says, what's the function values? Well, that just means when I plug -4 into my function, what y do I get back out? So if I plug in -4, it's that point, I get 1 back out. So I want you to notice, like the limit as x got closer to -4, the y value got closer to 1. Well, that's the same thing I got when I plugged -4 in. I got 1 back out. Okay, let's look at number 2. Number 2 says, what is the limit as x approaches -1? So now we're going to come over here. What happens as I get closer to -1? And if you look at that, that y value is getting closer to 4. As I come from the right side, same thing, that y value is getting closer to 4. Now I want you to notice that the point, the actual, when I plug -1 in, it actually comes out to be 1. But that doesn't matter for the limit. With limits, we don't care what's happening at the actual point. What we care about is what happens as I get closer to that point. So again, I'm getting closer to y equals 4. I'm getting closer to y being 4. So the limit is 4, but when I plug the actual -1 in, I actually get 1 back out. So that can be a little bit tricky. When you have a hole in the graph or a displaced point like that, your limit and your actual value may be different. Let's do the limit as x approaches 2. So I'm coming over here. As I get closer to 2, my y value is getting closer to 1. So I get closer to 2 from that side, my y value is getting closer to 1. So my answer is 1. Let's do number 10. What is f of 2? If I plug 2 into my function, there's just a hole in the graph. There is no point. So let's put over here it's undefined. Or we can put does not exist. Okay, let's do number 4. As x approaches 3, so if I keep going on here, I'm going to say what happens as I come down, I get closer to 3 coming this way. Notice how the graph's just going down. If I come down from the other side, graph's going down. They don't approach any number. So there's two things you could put here. You can put does not exist, like there is no limit, does not approach a number. Now, if you want to be more specific, you can say -infinity. When you say -infinity, it means that it does not exist, but you're describing that even though it doesn't exist, they are both going down. If I try doing f of 3, right, it's also undefined. Or again, you can put it does not exist if you want to. There is no value. When x is 3, there is no y value. Okay, let's do 5. As x approaches 5. So if you're thinking, if I'm coming along here, right, there's my point. As my point gets closer to 5, my y value is getting closer to, looks like -1 as I come from the left side. If I come up this way, as I'm getting closer to 5, my y value is getting closer to 2. So they're approaching two different numbers. When that happens, that means the limit does not exist. They have to approach the same number from both sides. What is f of 5? That one has a closed dot up here. So when I plug 5 in, I get 2 back out. So that's equal to 2. Hey, 6 and 7 are what we call one-sided limits. And that's when you approach the the x value from one side or the other, not from both. So if you look down here, that little negative up there, that means I'm approaching 5 from the left side. So come back over here. Now I'm not coming from both sides. I'm just approaching from the left side. So we're only looking, sorry, from the left side. We're only looking as I come this way. Oh, that's the right side. I'm sorry. As I come from the left side, as I get closer to 5, the y value is getting closer to -1. As I come from the positive side, so from the right side, my y value is getting closer to 2. Just to point out, in order for your limit to exist, for the limit of 5 to exist, those two right here have to come out to be the same thing. They have to be equal. You have to approach the same thing from both sides. If they don't, right, that's why we got the does not exist up here, because they don't approach the same thing. All right, hopefully that kind of gives us an idea about limits here. We're going to talk next about continuity. Continuity really means, here's an informal definition. I like what our book has here. It says if you can draw a graph without lifting your pencil off, that means, that means it's connected or it's continuous. The formal definition is this, is if its limit and the function value are the same. So if you look at this graph and where it's continuous, this graph was continuous at all the way through there. So it's continuous at -4. Well, I want you to notice when I plug in -4, I got 1. And when I did the limit as x approaches -4, I also got 1, right? As I come this way, it gets closer to 1. As I come this way, it approaches 1. And when I plug in -4, it's equal to 1. That means the function is continuous. So that's what that's saying on that official one, right? If its limit and the actual value are the same, then that proves or shows that it's continuous. So here's your definition of continuity. A function is continuous at an x value c if and only if, right, the left-sided limit is equal to the right-sided limit, which is equal to the actual value, the actual point. If all those things are true, then that proves that it's a continuous function. In this course, we're going to look at 3 main types of discontinuities. They're going to be holes, and we have examples of all those on that graph. We'll go back to it. We have vertical asymptotes, and we have jumps. There is a 4th type, which is called an oscillating discontinuity. They hardly ever happen. We're not going to really worry about that too much in here. If you want to, and I'll leave this up to you, you can grab a calculator and you can graph y equals 1 over x. And that's an example of an oscillating discontinuity. And you're looking at what happens as you get closer to 0 on that graph. Okay. So let's go ahead and name it says list the x values of the discontinuities. So if I go along here, right, the function is continuous as I travel along all the way until I get to there. Right there, I'd have to pull my pencil off the graph to do that. So that's when x equals -1. The function is discontinuous. Okay, the next one, right, it's continuous all through here until I get to there. At 2, I have to pull my pencil off. As I come down here, right, I can't get across that, so I have to pull my pencil off again. That means it's discontinuous again at 3. And I come up to here when x is 5. There's a jump there. That's also discontinuous. So those are all the points where it's discontinuous. Right, this one at -1, right here, there's a hole in the graph. At 2, there's a hole in the graph. I want to point out too is even if there's a point down here, we still consider that to be a hole in the graph. Or if it doesn't have a point, we still consider it to be a hole in the graph. At 3, we've got a vertical asymptote. And at 5, we call that a jump. Sorry, that was bad writing there, but we call that a jump or sometimes a break in the graph. So all these discontinuities we can basically put into 2 categories. The 2 categories are either removable or non-removable. Removable discontinuities occur when the function has a limit. So if it has a limit, in other words, if it's a hole in the graph, then it's going to be a removable discontinuity. If there is no limit, that means it's either a jump or a vertical asymptote, and that's considered a non-removable. So it wants us to tell which one of those are removable. So if you look right here, there's a limit at 1, right? It gets closer to 4, it gets closer to 4. It has a limit. That means it's removable, right? It's a hole in the graph. Right here, as I get closer to when x is 2, it gets closer to 1. So come from the right side, it gets closer to 1. so it has a limit, that means that it is a removable. The vertical asymptote is non-removable. If you look over here at 5, that is non-removable. There's a big jump there. So you're talking about removable or non-removable. If it's a hole in the graph, removable. If it's not, if it's anything else, vertical asymptote, jump, or break, then it's non-removable. The way I think about it is if I could plug one point in there and it would make it continuous, then we'd say it's removable. All right, so moving past that, if we just talk about functions themselves, so I don't have the graphs, I have the actual function. This is really important, but it's also really easy. If a function is continuous, then you can find a limit just with direct substitution. In other words, you can just plug the number in. The reason why, come back to here, if a function is continuous, that means the limit as x approaches -4 from both sides will be exactly the same as the value you get. So if it's continuous, I can just plug in -4, find that y value at 1, and I have my limit. I don't have to go through some more complicated steps. So this one, if you look at this, 3x squared plus 2 is a parabola. That's what type of graph it is. A parabola is continuous. So all I have to do is just plug 3 in. So I plug 3 into here. 3 squared is 9, times 3 is 27, plus 2 is 29. 16 is a little tricky because this actually is not a continuous function. And the reason why is because down here, x cannot equal -1. If I plug a -1 in there, I get a 0 on the bottom. But when we're finding a limit, I only care about the area around where we're finding the limit. What I'm trying to find as x approaches 1. So even though I can't, right, x cannot equal -1 on that function, there's going to be either like a hole or a vertical asymptote there. I'm not worried about that. I'm just going to plug in, because I'm plugging in 1. If it were -1, I'd have problems, but I don't. So plug in 1, I would get 1 plus 1 on top, 1 plus 1 on the bottom. So it comes out to be 2 over 2, which comes out to be 1. Okay, 17 is the limit of the cosine of 2x. Cosine of 2x, cosine function is a continuous function, right? We just graphed that in the last chapter. There are no breaks or holes or vertical asymptotes. So I can just do direct substitution. So to find the limit of the cosine of 2x, I'm just going to plug in the pi over 3 in. So 2 times pi over 3. So really that ends up being the cosine. Sorry, my board's being weird. Let me come over here. Cosine of 2 pi over 3. So let's see, 2 pi over 3. We got to go around 2/3 of the way around. That means this part, my reference angle right here, is 1 pi over 3, 1/3 pi. That means it's a 60-degree angle. So that side has to be square root of 3. This side has to be 1. That side has to be 2. That's a -1 actually. Cosine is adjacent over hypotenuse, so, or the x over r, so -1 over 2. So there's my answer. And again, the reason why I can do that is because cosine's continuous, so all I did is just plug pi over 3 into my function. Okay, and I got my answer. The ones that are a little bit trickier are piecewise functions. And the reason why is because a lot of times piecewise functions, let me just draw a quick example of a piecewise function. Let's say we come over here where x is 1. A lot of times what will happen is the graph will come up like this. There'll be a hole, and then it'll go up like that. So if that happens, right there, right at 1, there's a jump in the graph, and that means there is no limit. Now, it's also possible that it could be something like this, where the one side comes in, and then they meet up just perfect, and then it would be a continuous function, and it would have a limit. So here's a trick to checking piecewise functions. If you look at 18, right, it gives me the f of x. It says, what is the limit as x approaches 1 of f of x? Well, we have to worry about this when, if x is approaching the number where it changes from one graph to the other. So when x is less than 1, I'm graphing this one, right? When x is greater than 1, I'm graphing that one. And I'm trying to find the limit as x gets closer to 1. So what I have to check is it case number 1, like this one, where there's a jump, then the limit would not exist? Or is it case number 2, like this one, where the two graphs meet up? Because then the limit would exist. It'd just be whatever that value is. So there's kind of a harder way to tell, and there's an easier way to tell. The harder way to tell is you can actually graph these. That takes a lot of time. And it's hard sometimes to get our graphs perfectly accurate, especially if it's not linear. So instead, what we can do is we can just check to see, do they meet up at the same spot? So when x is 1, right, when x is 1 right there and right there, do they meet, is it, they meet up the same spot? Okay, great, that's case number 2 then. If not, it's case number 1. So to do that, it's actually really easy. All I do is plug 1 into my first equation and plug 1 into my second equation and see what I get. So when I plug 1 into my first equation, I have 4 minus 1, which is 3. When I plug 1 into my second equation, I get 4 times 1 minus 1 squared. So that'd be 4 minus 1, which is also 3. Hey, I got the same y value. So when x was 1 and y was 1, they met up in the same spot. That means the function is continuous. That means it does have a limit. And we know what the limit is because it's whatever that value is when I plugged 1 in. Well, when I plugged 1 in, I got 3. So there's my answer. Let's look at 19. So this, again, we want to find out, is it case 1 or case 2? Is there a break or is it continuous? So we're going to start by, we're going to plug, and it says x approaches 1. So we're going to plug 1 into both equations. This top one I'd get 3 minus 1, which is 2. On the bottom one, I would plug 1 in, I'd get 1 squared is 1, 2 minus 1 is 1. Okay, so that means when x is 1, when it transitions from the one graph to the other, they don't have the same value. So that's going to be like case number 1 up here, right? There's going to be a break and there's going to be a jump in the graph. So as I come from one direction, it's going to get closer to 2. If I come from the other direction, it's going to get closer to 1. And that means the limit does not exist. DNE does not exist. Look at 20. So we're using that same function g of x. This is a little something you have to be aware of. It says for the same function, find the limit as x approaches -1. All right, so if I come back over here, just think about my graph for a second. If I'm trying to find as x approaches -1, that's over here somewhere, right? Either, I don't care what my graph looks like because it's not in the transition. It's not here and here. I'm looking over here and over here. So I don't have to worry about on that one for checking to see if it's continuous or not. I just have to plug it in the right place. And -1 is right here, right? -1 is less than 1, so all I do is plug my -1 in there. So that'd be 3 times -1 would be -3 minus -1 cubed is -1 minus -1 changes to plus, so -3 plus 1, -2 is my answer. But you just got to be careful. The only time you have to worry about checking to see if it's continuous, like it is here, or if there's a break, like there is in that case number 1, is if you're plugging in the number where it transitions from one to the other. Right? We're plugging the number where it transitions from one part of the piecewise equation to the other one. All right, hey, the last part is this greatest integer function. It's kind of an interesting to look at, think about. It's also sometimes called the for function. You'll see why in just a second. The symbol for it is this. So it looks kind of like an absolute value, but it's got those lines underneath. It says the greatest integer, what it means is the greatest integer less than or equal to x. So for example, if I were plugging some numbers in there, let's plug some numbers in. Let's say I go like 0, 0.5, 0.6, 1, 1.2, 1.5, I don't know, 2, 2.1. So if I plug numbers in, this is what happens. If I plug 0 in, I want the greatest integer less than or equal to 0. Well, 0 is an integer, so if I plug 0 in, I get 0. If I plug 0.5 in, I want the greatest integer less than 0, or sorry, less than 0.5, which is 0. The greatest integer that's less than 0.6 is still 0. Anything it will always be 0 until I get to 1. Once I get to 1, it jumps up to 1. At 1.2, you round it down, it's still 1. 1.5, it's still 1. When I get to 2, now it jumps up to 2. And then 2.1, and it stays at 2 until I get to 3. So that's why it ends up looking like this, right? At 0, it's 0 all the way across. When I get to 1, it jumps up to here, goes across. I get to 2, it jumps up to there and goes across. So you're always rounding down, and that's why they call it the for function, right? It's the bottom, because you're always rounding the number down. So it wants me to find these limits. It says, what's the limit as x approaches a half of the greatest integer? So if I plug in a half, you can look at the graph right here. A half is right there. Well, if I approach from the left side, it's 0. If I approach from the right side, it's 0. So the answer is just 0. 22 says, what's the limit as x approaches 1? This one's a little bit trickier. If you look up here, if I go along the graph, as I get closer to 1, I'm getting 0 from the left side. If I get closer to 1 from the right side, I'm getting closer to 1. So this, from the left side is 0, from the right side it's 1. That means that the limit does not exist because they're approaching different numbers. So that's another example that kind of an interesting case where you can do limits with and some different things happen. This really is just an introduction to limits. We're going to keep talking about limits. These next few lessons, you'll keep seeing them pop up over and over again. It's a really important concept to understand. So pay close attention. If you have questions, make sure you let me know, and we'll go through those and make sure we have a good understanding of it. Thanks, guys.